So the first one I have x times x. I believe I can write it as x times x, and the other one I can write as x times 1. That's by natural exponents on the first one. And I know this is by multiplicative identity. I can always get a 1 for free. If there's nothing left over, I can always say multiply by 1. And now I can say, wow, it looks like someone distributed an x out of both of these. So I can undistribute it, and I have x plus 1 using the distributive law. And what I've done is I've written the polynomial as the product of two items. That right there is what we call factoring. Okay? And what we did here is factor out the greatest common divisor. Pretty easy, right? Want to try it again? Let's try it with this one. So on this one, again, sometimes you can just eyeball it. 5x, what would be left over if you factor out a 5x? It would be a 2 and an x there. If you factor out there, what would be left over? Well, nothing, but you can't have nothing. You can get a 1 for free using the multiplicative identity. And so I use a 1 as a placeholder here. And now I can see, wow, it looks like 5x was distributed to both of these. So I could undistribute it, and what would be left in there would be a 2x plus a 1 using the world famous distributive law. What I've done is I've taken the polynomial, which was a sum of two terms, and I wrote it as the product of two items. That process is called factoring, when you write as a product of two items. Factoring. Easy, right? I make this stuff look easy. That's why they pay me. Let's try it again. This one, again, you can eyeball it. Here, if you can't eyeball it, I suggest you prime factorize. This is a 2 times a 5 times an x times an x times an x. This is a 5 times a 5 times an x times an x. Those are the prime pieces. This makes it really, really obvious what's common. This is common, that's common. This is common, that's common. And there's nothing else that's common. So a 5x squared is what's common. And so I could rewrite it like this. I could say 2x times the common thing would be a 5x squared. Here there's only a 5 left times the common thing of 5x squared. This is just by inspection. This is times table and natural exponents. And now I can see exactly what's common, a 5x squared and a 5x squared. So I could say, whoa, it looks like someone distributed a 5x squared. If we go on and undistribute it, you could say this is 2x plus 5 using the world famous distributive law. There you go. Prime factorized using the distributive law. Super famous. Okay, let's try it again. Do another one. Let's take it up a notch or two, yeah? How about this one? You have 3 items and you have a bunch of x's and y's and coefficients. How do you know what's common? Well, first of all, I don't like this subtraction. I always like to change mine to addition, so I'll say change that to that by definition of a minus b. And now I'm going to try to look at the prime pieces. This is 24. That's an 8 times 3. So that's a 2 times a 2 times a 2. That's an xxxx xx y plus negative 40. That's a negative 1 times, let me think. That's 4 times 10. The 4 is 2 times 2, and the 10 is 2 times 5. And xxxxx, that's 4 of them. Y, that's 3 of them. 4 times 4, that's 2, 2, 2, 2. That's a 4, and that's a 4. 4 times 4 is 16. Xx, y. Now I've prime factorized it. Again, if you can just eyeball the GCD, by all means do it. But if you want the professional way to do it, this is the professional way. Because now I can just take a look at here and see what's common. I see y square, y square, y square. So I'm going to circle a y square from every one of them because they all have the y square. Okay, and then I'm going to try to find more things that are common. How many x's are common? This one's got a whole bunch, that one's got a whole bunch. This one's only got 2 x's. So I think this is the most limiting one. The x square. There's no way I can take more common x's because there's no more common ones, just 2 of them. Then look at the 2's. I see I've got a bunch of 2's, a bunch of 2's, a bunch of 2's. I'm going to go with this many 2's, 3 of them. This many 2's, this many 2, that's common. So here now I've got left 2's and y's. Here I've got negative 1, 5 and x's. Here I just have x's. So there's nothing else that's common. That's as good as it gets. And so the thing that I'm going to factor out of everything would be an 8x squared y squared. That piece, that's the 2 times 2 times 2, that's the 8. X times x, that's x squared. And the y squared, that's y times y. And I'm going to try to see what's left over. since I had 3 items here, 1, 2, 3, 3 terms, I should have 3 terms left in here. So the first one would be x to the third, because I got 3 x's left. Next one's going to be a negative 5x, negative 5x. Oh, and a y there. I see a y there. And the next one is going to be, let me see, I have a 2 and y to the third. And I do a real quick check to make sure that I did it right. So if I multiply these two, that gives me 16 and 5 y's and 2 x's. That checks off. Then I check the next one. 8 times 5 is negative 40. I've got 3 x's. You see this, I made a mistake. And I've got 3 y's. Perfect, that checks off. I had 2 x's here. That's why I needed 2 there. Just checking to see if you're paying attention. Now the next one I've got 8. See, I had left a 3 here, 3 there, and I've got 5 x's and a y square, and now it's perfect. Okay, that's how you you do the work and you check your work to make sure that you did it correctly. If I distribute this, I get exactly this original expression. The act of distributing this and multiplying it, that's the way of checking your factorization to see if you did it right. And it looks like we got a perfect one here. That'll wrap it up for us. Alright, we'll see you guys next time. Peace.